Okay, so last lecture we defined the singular value decomposition of a matrix A as U sigma V transpose, and we gave some of the properties of U and V, namely they're made up of a generally non-square matrix of orthonormal vectors, so that U transpose U is equal to the identity matrix. U transpose U is equal to I. And V transpose V is equal to I. But in general, U transpose is not equal to I. We'll talk more about that later. So we have this type of thing, and then we have, of course, the sigma is diagonal. With the singular values in there. Okay, so if we come along and do something like this, A transpose A, and B, V transpose, actually, the transpose goes away, and when we transpose a diagonal matrix, we get it back. And then multiply it by A, and this right here as we've already defined is going to be the identity matrix, so we'll get V sigma squared V transpose. So some interesting things to note here. This actually tells us quite a bit. First off, this is going to be symmetric. And it's going to be positive semi-definite. We don't know if it's positive definite because some eigenvalues could be 0. But we do know that it has no negative eigenvalues because of the way it's built, how it's a product of two matrices, essentially two matrices squared. So some eigenvalues could be 0, but at least it's positive semi-definite. We've already pointed out that that's the identity. Okay, so here we have the sigma r's are the square roots, positive square roots, of the eigenvalues of A transpose A. Because with A transpose A, we just have our symmetric, positive, in this case semi-definite matrix. And so we know we can decompose it into some matrix of eigenvalues, V times the diagonal matrix of the eigenvectors times the diagonal matrix of the eigenvalues times that eigenvector matrix transpose. And so we can then relate this right to the of A transpose A to our previous decomposition. I should also note that the sigmas are the square roots of the eigenvalues of that, but it's actually of the non-zero eigenvalues of that. Okay, well, we can do the same magic trick, and we can show that A transpose is equal to U sigma squared U transpose. And just observe that non-zero eigenvalues of A transpose A and A transpose are the same. So the sigma r's are also the square roots of the corresponding eigenvalues of A transpose. Okay, so let's look a little bit more into detail here. As we've discussed, this works for non-square matrices. So we have A is m by n, and in general, if m is greater than n, greater than or equal to n, then R is the number of linearly independent columns and if m is less than or equal to n, then R is the number of linearly independent rows. And then correspondingly, A would be full rank, if R is equal to minimum mn. So you find your smallest dimension, and along that dimension, if you have that many linearly independent rows or columns, then by definition a non-square matrix is full rank. So let's look at some examples and how this actually applies. So let's assume we had a tall, skinny A, well, we'll have a tall, skinny U, a small sigma, and potentially a short, fat V. So in this example, we could have, this might be 6 by 3, 3 by 3, and V would be 4 by 3. So V transpose would be 3 by 4. As such. And so in this case, what do we have here? We'd have, this is 6 by 4. Inner dimensions in multiplication cancel out, giving us our 6 by 4 matrix. So in this case, we have m, number of rows, is greater than the number of columns. And so y equals ax. We go back to that. We essentially now have, in this case, maybe 4 dimensional x, and yet we have 6 observations of x. And so in this case, our system of equations is overdetermined. Yeah, so let's put this here. X is 4 by 1 and y is 6 by 1. Okay, sigma could be, in this case we had 3 by 3, it could have been 4 by 4. It could have been 1 by 1. Lots of different ways that this could have played out. Now let's go with a short fat A. And maybe U sigma V transpose. So if we have M is less than N, actually, let's see if we, let's just put numbers to this. Let's put 4 by 6 just for kicks. Then that's 2 by 2. And so V transpose would have to be 2 by 6. And this would be 4 by 2. So my drawing isn't quite to scale, but that's okay. We just keep going. So in this case, y equals ax is underdetermined. In other words, we don't have enough observations to fully explain the data. And finally, let's say we had a full rank square A. In that case, we would have a square U, square sigma, square V transpose, and M is equal to N, and if it's also equal to R, it's full rank. And A is square, and there we go. Okay, so different ways that the SVD can manifest. And we'll be looking at solving our y equals ax in both these circumstances, one where we have overdetermined and the other where we have underdetermined.